Yeah, you have to go Aidite, Facebook, Aidite. Yes, of course. From Aidite Technology Ltd, there will be the link. Mm. Mm-hmm. Yes. Yes. Yeah. Bye. This is what is going on now. Yan, can you confirm that you can hear my voice? So I can proceed? Yan? Hello? It's okay? Can hear, good. So, we start this webinar. I am Lamberto Villani. I'm in Dubai. I have a dental lab. And today the lecture will be goodbye to chipping with zirconia restoration. And I give also some suggestions for the bonding protocols and some materials. Today the zirconia from 2004 changed a lot in composition, in aesthetic properties, and is still growing fast, very fast. This is a slide that I like. I really like, because this is 4 billion years ago. The Eden is a geologic eon, as you can see on my writing. It began with the formation of the Earth about 4.6 billion years ago. And the mineral, the zirconia, is made from the mineral zircon. It's a very special mineral, one of the first mineral formed 4 billion years ago in an Eden eon. This was when the solar system was first created and the Earth was still, it was a rock. So what is zirconia? Zirconia is a ceramic made from mineral zircon. Zircon formed in the Earth's crust about 4 billion ago. The zircon is a zirconium silicate. As you can see, the formula with the radioactive elements was the meaning. After we'll see. Zircon is found on every continent. The most economical mine is in Australia. This is just for information. But we have to now focalize on these different names, because there is a much public confusion between these four materials. There are zircon, zirconia, zirconia, and cubic zirconia. What are the differences? Oh, now zircon is a naturally occurring mineral. What I showed you before, it was 4 billion years ago on the Earth. Zirconia is a silvery white metal and a chemical element, meaning we can find in the periodic table. Zirconia is the white crystalline oxide of zirconium with a chemical composition of ZrO2. A naturally occurring but rare form of ZrO2 is the mineral Aidite. It's found in Brazil. Cubic zirconia is a synthetic gemstone. Actually, is the poor ring that you can buy for your girlfriend because you have no money, because it's very similar to the diamond, and it sells for a tiny fraction of the cost of diamond. All these materials are related. Zirconia, cubic zirconia are all produced from industrial grade zircon. So when a patient is going to the clinic and is saying, I'm going to have a zirconia crown, doc, or the doctor is proposing, I will order a zirconia crown for you. Really what they are ordering is a zirconium dioxide. It's a blend of heavy metal zirconium from the periodic table with oxides. It has an atomic number of 40 and the atomic symbol of Zr. And when they mix, they become ceramic material. Somebody say, oh no, zirconium dioxide is a metal-based. It's a metal-based, of course, before becomes an oxide. And by definition is a non-metallic substance. Now the cool about this material, that is very, very stable and very, very strong. Actually gets stronger as it gets stressed. Like with your bear, you are going to grind heavily, it will get stronger. It's all called transformational toughening. And as you are going to apply pressure on force on the zirconium dioxide, the oxides are getting to cross-linking of the material, which eliminate further propagation of the fracture. We will see later. So it's okay. All this explanation is okay, but what is in details zirconia? It's a ceramic oxide, it's not a metal, whose crystals are arranged in a crystalline structure. You can see here, this crystalline structure has advantages, but also disadvantages, because according to the temperature, it has different crystallographic phases. In fact, we have a room temperature. It is a monoclinic phase. By heating up to 1170, it transforms in tetragonal phase. That is the strongest. That's what we want to work on. By heating more, 2370 degrees, it transforms into a cubic phase. The real problem with zirconia is that it is not a stable material. And when it cools, it tends to return to the monoclinic state, with mechanical problems related to dimensional changes. So, how do we use zirconia at room temperature? By keeping it in a tetragonal state. Using dopants, meaning some dopants, as for dental use, the yttrium, the oxides, maintain the tetragonal structure even at room temperature because of the yttrium inside. If the zirconia is not stabilized, it tends to return to a monoclinic during cooling. And in this step, it increases in volume up to 4–5%, causing catastrophic failures. So to get the stable material that can be used in dentistry and medicine also in general, the zirconium dioxide is stabilized by adding from 3 to 5% of yttrium in tetragonal phase. This very small amount of yttrium inhibits tetragonal to monoclinic transformation below 1170 degrees, allowing the presence of tetragonal phase at the room temperature. But this tetragonal phase is only partially stabilized, and under stress applied to the surface, like a burr, can transform into monocline phase again. That is why this material is called yttrium partially stabilized zirconium dioxide. So the reason we need the zirconium dioxide stabilized in tetragonal phase is because in tetragonal phase the material is white in color and has excellent mechanical properties. Sorry. So after we take out our bridge from the furnace after the sintering, this is the baking that all the brands of zirconia suggest you before you build up ceramic. And they call, some of them, they call this baking, they call zircon clean. But actually is not a cleaning. You are not cleaning. We have a good steamer to clean. This is to stabilize, as you saw before, to stabilize the structure, to stay in a tetragonal phase. Zirconium dioxide is a very bad heat conductor, meaning it's taking long time to take heat, and it's taking long time to release after baking the heat. So what's that mean? It means that when you are going to fire ceramic on a zirconia dioxide and you are putting 45 degrees per minute, it's too fast for the zirconium framework. It will not reach so fast the temperature. It needs long time to take the heat. So when you have actually after baking the ceramic on your framework, you have ceramic very well baked outside, but inside, because of the bad conduction of the heat of the zirconia, you have still ceramic not very well baked, so you don't have a very good bonding. Because there is, somebody say there is no bonding between zirconia dioxide and ceramic. No, it's not true. There is a bonding if, just if, you make a foundation baking. What's mean? The foundation baking that are doing other, like Ivoclar for the, before you build up the Emacs. This is the foundation I'm doing in the zirconia. Why I'm doing this? Because it's taking time to take the heat. So I will preheat the temperature 450. I will dry 6 minutes. Then I raise 20 degrees per minute, not 45, 20. I will use vacuum for my ceramic, of course, because it's a foundation. With the foundation you can use a small amount of dentin mixed with some staining, and depends on the system, ceramic system you are using. But it's very important. Give to any baking between framework and ceramic 20 degrees per minute. The foundation, I will go to the final temperature 980. It could be enough 950, but I want to be sure. I have 980, 0 minutes, but I have to cool down very slow until 500 or 600 degrees. In this way, I have the first real bonding in my ceramic with the zirconia framework. Oh, this is another white chipping. It's something of the past, because with this baking that I showed you before, the foundation, and then you bake all the ceramic with 20 degrees per minute, and always you go down slowly, cooling down up to 500 or 600 degrees. This is one suggestion to avoid chipping. Then there is this, my very nice friend Nondas, that is giving, with a good reason, is giving this kind of shape for the zirconia framework. Dr. Fisher, in it was in maybe 1970, he shows that any ceramic baked inside the concavity cannot have any fracture. In fact, if you see here, there are you have to create all around concavity. So with this concavity, also here in the buccal side, everywhere concavity, you avoid 90% of the fracture, because it's easy to understand why. Any fracture we see on the ceramic, it's transversal to the cusp, vestibular or palatal. It's where is the convexity of the shape of the metal or of the framework. But you never saw a fracture inside the fossa. So Dr. Fisher saw in 1970, I don't remember, 76, he saw that inside the cavity, the ceramic is developing a big force, a big power, so it will not break. The properties of the zirconia material is determined by how much yttria is added, how and when the yttrium is added, the particle size, the grain of the zirconia itself, the process used to make the powder, how the discs are fabricated. That are the most important things. Why? That's why most of the time when you look at the same color A2, for example, A2, but on different brands, they look different. Why? Because they use different processes, different quantity of yttrium, different particle size, and so on. So the zirconia dental composition is yttrium from 5 to 10%, but determines most of the properties, the toughness and the MPa. There are also hafnia. This is the sister material. You will always find hafnia from the zircon, the mineral. Doesn't make any difference. And the alumina that we add to prevent aging. Some milling suggestion. Calibrate the mill frequently. Check the mill strategy you are using. If you are getting chipping, then slow the feed rate or change the tools. Check the tools for wear and replace when your software recommends a change. Keep the disk support free of zirconia dust. This is very important because if you have some dust where the disk is sitting on the nest, it will be a problem. Then I take some information from Dr. Gordon Christensen, and this is recent, it's October 2018. I found these 5 common mistakes to avoid, very interesting, very helpful. Mistake 1. When the dentist give us inadequate tooth preps and impression, meaning avoid shoulder 90 degrees margin, it will never sit as good as a chamfer. And in the occlusal, always give 1.5 space for the ceramic. This is what we want. We want a nice chamfer and 1.5 all around the occlusal. Mistakes 2. Inadequate surface area, roughness of zirconia internal surface. The zirconia cannot be etched using hydrofluoric or phosphoric acid. CRA, that is clinician report article, suggests not to glaze the zirconia, but rather just polish the surface. With the cycle of the occlusion, day by day, the glaze will go. And you will find the opposite tooth, it will find the rough zirconia. Consider for prep less than 4 mm axial height to reduce the digital die spacing, so the tooth will sit better, more contact. Mistake 3. Incomplete decontamination after restoration try-in. It's important in the clinic they remove saliva from internal surface of crown. We suggest IvoClean, followed by a true 1-minute rinse. Very important if you want to success in cementation. I suggest also to sandblast the internal crown, inside the crown. It's enough 1.5 the power of the bar. 1.5 bar, it's enough, and you clean with 50 micron sand. Fourth mistake, misunderstanding of primers. Seal-line only primers do not work on zirconia. Primers containing MDP can enhance adhesion. These are some examples of cement: Zeta Prime Plus, Clearfield Ceramic Prime Plus, Monobond Plus. Fifth, improper use of cement. So for preps more than 4 mm axial height, use RMGI cement. RMGI is a resin modified glass ionomer. For the preps less than 4 mm axial height, use self-adhesive resin cement. I don't know if some of you has experience an answer from your dealer, from who sold the sintering furnace for you. No, you cannot calibrate your machine because it's already calibrated. It's auto-calibrated. Okay, I don't trust. I buy these rings, are zirconia rings. They are called the process temperature control rings. You put this ring inside the furnace. At this moment, before you bake, they have 20 millimeters of diameters. After you take out from the furnace, the sintering furnace, at 1450, 1500, whatever is the temperature that you are using for your zirconia, you will check with the high precision caliper. You measure, and this measure here, 18.6, you are going to see on this table, it's the value 18.6 is roughly here. You are not 1500, but you are 938. This is a good way to calibrate. And now I finished to bother you. I will go to see this case that I made in here in Dubai. It's a dental assistant, and she has not a very good situation in the mouth. As you can see, she has a bridge and one crown on the 21. Big recession, gingival recession. So she wants to redo everything. In this case, we have dark prep, but doesn't matter because we have a lot of thickness. This is the model. As you can see, I trace this line, this blue line, to reconstruct the arch, and here in the two canines I can see there is space, so the two canines are inclined inside lingually. This is the future bridge. We use always this kind of material. From when I used this 3D Prozir, I was amazed when I used the first time. I was thinking, no, that's not possible. I have so good material, so nice chroma and nice translucency. So when you see in these slides, the two canines are hidden behind the two laterals. So that's why after you will see two veneers on these two canines to be an arch. This is black and white to see the value, but still the two canines are bothering me. So I want to make something. And these are the two veneers that I made with the cameo from Aidite also. Now the patient is very happy. We can see the totally different size of the restoration. We start from here to reach this nice effect. This is monolithic. It's totally 3D Pro without any ceramic on top. There is no build-up. Also, the two canines are matching all the surrounding teeth. It's a very nice material. When you have to do this kind of work, anteriors, it's really nice. Here you can see the change of the face. And I take out the incisal edge because she was inside the vermilion. This is the final. This photo I make just to really show you how amazing is this material. Look in this photo, is really matching the natural enamel, the natural translucency we have in the mouth. Also here. Here I put the shade guide to compare, and of course I have a darkness here due to this metal of the shade guide. So what I did, I removed the metal, and it's really fantastic matching. Fantastic. This is A2, sorry, A3. Nothing, I don't know, I have no words to say how is beautiful this material to match the same of the shade guide. So this is a teamwork. You know better than me, we need the teamwork. We need to see the patient as a technician. We need to know what the patient is waiting from us. We cannot just receive two impressions and do the anteriors without any mock-up, any wax-up. And thanks to Aidite, today I have really switched to 3D Pro Zero because it's giving me so much satisfaction. Not only for me, also for the doctor here, Dr. J, on the right, on the left, and to the patients. So thanks to here, we finish early. But if you have any question, I'm here. And now I invite you to see this video clip of Aidite. Thanks a lot to see this lecture. Okay, so I have a question here from Ryan Oringo. The question is, on the case presented, did you use any staining? Yes, I used Mio, the new staining from Jensen, and it's very, very nice and good combination with Aidite. If we have other question, Mrs. Diane. So I didn't realize that this lesson was so short. So I make you sure next time it will be longer. We will make minimum 1 hour. Okay. Thank you very much.